Okay, I wanted to talk a little bit more about center of mass, and I wanted to give you sort of the formal definition. So, center of mass is basically the sum of all the mr squareds in a given piece of a given like object. So, let's say um, you had four balls, M1, M2, M3, M4. Let's say that M1 is 9 kilograms, M2 is 10 kilograms, M3 is 11 kilograms, and M4 is 12 kilograms. And let's say that the first ball, M1, was at 3, 2. So this is where M1 is. So it's at 3, comma 2. And let's say that over here at 2, comma 4, that's where your M2 is. And let's say that M3 is over on this left side at negative 4, 1. So it's at negative 4, 1, and this is M3. And then M4 is at negative 2, negative 5, let's say. M4 is at negative 2, negative 5. Okay, so as you know, there is a center of mass. We've talked about that. And the center of mass, if you remember, is found by doing m1 x1 plus m2 x2, etc., and then dividing by m plus m plus m, right? You remember. Then you do the same thing for the y's. That's called COM. Okay, we're not really looking for COM here. What we're looking for is if this was all connected somehow. Let's say you could draw it like this, like a box, or if that's too hard to understand, you could basically draw segments like this. What we're doing here is we're not calculating center of mass, although we could. We're just not doing that right now. Instead, what we're doing is we're saying, okay, suppose you were standing at the origin, and this little person, see, and let's say that these were plastic pipes, four of them, all aiming different directions, all with different lengths. Pretend the pipes themselves are very, very light, so they're not very heavy, but the balls themselves are. As you know, the balls are 9, 10, 11, 12 kilograms, you see. So, as a person in the middle, how hard would it be for you to twist this whole setup? Or more specifically, how hard would it be for you to rotate, or how hard would it be for you to change the spinning speed is the right question here. So to slow it down or to speed it up. Okay, so when we ask this question, we're finding I. It is very important that you pick a starting point for the person to be. So in this particular first example, I'm doing 0, 0. And this is very easy to do as long as you understand what the letters mean. So unfortunately, the R's that I'm writing up here, those are not the X's and they are not the Y's. Unfortunately, those are the lengths of the red segments. So you do have to kind of think about this a little bit. How long is R1? How long is R1? So R1 is this segment here. How long is that thing? And so you can do Pythagorean theorem if you like, or you can just kind of, you know, do the distance formula from Math 1. Remember that thing? So R1 would be square root of something squared plus something squared. And inside, if you remember, you're supposed to do y2 minus y1 squared and x2 minus x1 squared. So we're comparing to the origin. So it's basically just 3 minus 0, 2 minus 0, and then that's squared. It's square root of 13. For R2, for this time, you're comparing the M2 location to the origin. So that'd be 2 minus 0 squared, 4 minus 0 squared. And that is square root of 20. For R3, you use the coordinates of the third ball and so on. So negative 4 and 1. So it's negative 4 minus 0 squared, 1 minus 0 squared, and that's square root of 17. And then lastly, we have R4. They're all basically the same idea, but you kind of have to know that these are hypotenuses. They're not really x's or y's, right? So the last one, of course, is M4, and that's the negative 2 and the negative 5. So just being very careful to put all this in, and with all those extra minuses and everything, just got to be kind of careful here. Okay, so feel free to request a pause there if that was a lot of writing for you, but this is what I got. Okay, now these are the R's, and the formula is at the top of the page. So the formula is I'm supposed to take 9, 10, 11, 12 and multiply them by R squared. So the moment of inertia, if you're standing at the origin rotating, is 9 kilograms times rad 13 squared plus 10 kilograms times rad 20 squared plus 11 kilograms times square root of 17 squared, and lastly, I think it was 12 kilograms times square root of 29 squared. And this gives you one big number, whatever 9 times 13 plus 10 times 20 plus 11 times 17 and so forth is. So I'm going to type that into my calculator behind the scenes here. Just bear with me as I get you a number. So it's 9 times 13. We have a 10 times a 20. That one's easy. We have an 11 times a 17, and we have a 12 times a 29. Okay, 562 it is. 562. Now this units is kind of weird. It's kg m squared, kg meters squared. Okay, now if we decide to move our person somewhere else, then unfortunately this changes the length of all 4 red segments, right? So if we move, let's say, the person from the origin, we're like, hey, you're not going to stand there anymore. We're going to have you stand somewhere else and build your pipes together there. So let's say now you put the person at, I don't know, -2, -2. So now the person's here, see? Some of these sticks just got shorter and some of these sticks just got longer, you see? And we're still trying the same thing to change the spinning speed of this mess of stuff. So because each segment is different, it will affect the whole answer. Okay, so now the person's at -2, -2. And so we're going to have to kind of start all over again, unfortunately. Isn't that terrible? So you would do I -2, -2. You would still have the 9. You would still have the 10. You would still have the 11. You would still have the 12. The difference would be the rads, So you kind of start over. All of these zeros that you see here, all of these would be -2s because we're at the point -2, -2, not at the point 0, 0. So you kind of have to start all over again, but not use 0, 0 here. These would be -2s, all of them. Ew. So I kind of need to start over, don't I? Okay. So a little bit of work here. R1, R2, R3, R4. And these are all the same idea. I'm going to go a little bit faster, kind of in my head, And for M1, that's this and this. If you subtract the x's, you get 5. If you subtract the y's, you get 4. That was 5 and 4. That means there's a 25 and a 16 here. Looks like we have a rad 41, and that would go in my first spot for R. Then I would go to R2. So R2, since our person is at this new location, R2 is between -2, 2, -2, -2, and 2, 4. Subtract the x's, we get 4. Subtract the y's, we get 6. I said 4 and I said 6. So that would be a 16 and a 36 right here. So that's square root of 52. And that goes here. Okay, next up is R3, the new R3. The new R3 is if we connect from our new center to M3. Subtract the x's, and we get -2, subtract the y's, and we get 3. I said -2, and I said 3. Squaring those gives me 4 and 9. So this would be 4 and 9. If I'm going too fast for you, just understand that I'm just doing distance formula from Math 1. And then lastly, R4. R4 would be connecting our center of rotation, -2, -2, to this point, -2, -5. When you subtract the x's, you get 0. When you subtract the y's, you get -3. I said 0, and I said -3. So you square those to get 0 and 9. So these would be a 0 and a 9, so it's square root of 9. Okay, so we actually have everything we need. We have the 9, the 10, the 11, the 12. We've got the rad 41, the rad 52, the rad 13, and the rad 9. And that's everything you need, my friends, to find the moment of inertia. So again, I'm going to get my calculator. This time it's not 9 times 13 plus 10 times 20 plus 11 times 17 times 2 times 29. It is 9 times 41 plus 10 times 52 plus 11 times 13 plus 12 times 9. And that is 1140 kg m squared. Okay, so the first time I did this, I got 562. The second time I did, I got 1140. What does that mean? So that just means the first person that we drew who was standing at the origin, it's like twice as easy for that person to speed that thing up. But this guy, he's going to have to basically push twice as hard to get the same sort of alpha going. So that's what it means. And that's how you do it when there's 3 objects or 4 objects or 5. Okay, this is called discrete, when you have this object and this object and this object and this object, and you can actually count them. We call that discrete. If we connect all of these into like a smooth ribbon or something, and let's say this is completely filled in, this too has an eye, you see. You see. In other words, if you could put an infinite number of balls in here, some big, some small, some big, some small, if you kind of squeeze them all in here like this, we wouldn't really call this discrete anymore. If it's really jam-packed full, we would call it continuous. Now, it's debatable whether this really exists in nature. We know everything's really made of chunky atoms, but sometimes the best thing to do is to pretend it's smooth. Now we would use calculus. So instead of sigma mr squared, instead of adding a certain number of individual mr squareds, instead what we would do is we would use calculus. And so we would switch to this. And it's actually r squared dm, not m dr squared. It's r squared dm for the reason that each mass is a tiny mass, a dm mass. Okay, this integral is fairly hard to solve, and there's a couple of things you need to remember. Whenever we do an I question, the origin is, excuse me, the center is always given, see? And very crucial in what the final answer will be. So I cannot just ask you where is, what is the I? That's not a fair question. I have to pick a spot, put you there, tell you, hey, spin this thing around from where you're standing. See? I want it to spin around this pole, so to speak. There, spin it around this pole. I want to see that thing accelerate. So actually, you probably wouldn't stand there, right? You'd probably tie it to the pole using rods that these rods don't have any mass. They're like plastic pipes. They're real lightweight. And you'd stand over here and you'd give that a shove, try to get that acceleration going. And where we put the blue line matters a lot. Matters a lot. We could even, if we wanted to, we could even put the blue line. You're probably guessing what I'm about to say. You could put the blue line over here and then attach this, secure it using plastic rods with the effort. The goal is to get this to go around this pole. So there's this big blob ring thing going around this pole. That's more of a revolution than a rotation, but the principle is the same, and we would still use this integral. The goofier the object, the less consistent the densities within the object, and the location of the object all contribute to how difficult this integral will be. So the really hard ones have a goofy shape with a weird density and in a location that's not convenient. Symmetry is always your friend when you're doing integrals, so the easiest thing to do would be to spin it around its own center of mass, to be honest. Okay, so what kind of integrals would I expect you guys to do? Well, probably not a lot, not a lot. Um, so let's say that you had a stick. I'll just do like a simple one. Let's say you had a special stick, and it looks like a regular stick, it really does look like a regular stick. But for some reason, it's right here, it's like jam-packed full of atoms. And then it just starts to kind of get more and more kind of mellow. Another way to say it is it's, it looks like a cigarette. Uh, Basically, right here, it's really dense. And then here, it's like not dense. And then in the in between, it's like getting denser. You know what I mean? Getting denser. So let's say this was density 71 kilograms per meter, and this is density 32 kilograms per meter. And in between, it's, fractions thereof. So like, 70, 68 and things like that. Okay. Notice I don't use the traditional density that you use in chemistry, kilograms per meter cubed, because this isn't really a box. It's just like a line. And so if I chop off this little piece, it's 71 kilograms per meter. When you buy this at Home Depot, you buy it by the meter. So it's like a simplified version of density that you learned in the past. Okay, so that's called a linear density. Some people like to use this Greek L for linear density. So let's say that those are the linear densities on the ends, and let's say that the actual linear density function looks something like this. Oops, sorry. Uh, okay, so this is the linear density function. Now you can plug in any x you like. Let's say that this is x equals 0, and this is x equals 5 meters long. So I didn't tell you that, but it's a 5-meter stick. And basically, this is a really cool little function. You could plug in like, let x equal 2, and that'd be like right here. And then you just put that in there, and lo and behold, you now know the density at that location. Let's see what that would be. Negative 39 fifths times 2 plus 71. Negative 78 fifths plus 71. 78 divided by 5 is 15.8, I believe. Or no, it's negative 15.6. And then you're adding 71. Okay, so I think it is 55.4, if I'm not mistaken. And that's the density at this blue location. X equals 2. So that's the idea, you see. And the density function allows us to not worry too much about individual densities, but just to think of it as all sorts of densities given by this equation. Okay, do you remember when I told you that I was the integral of r squared dm? Okay, the dm is a little bit tricky. So we know that mass of the whole rod, right, is going to basically be um, the density of the rod times the length of the rod. The density of the rod times the length of the rod. So to some of you, that would be really obvious. To others, it would not be obvious. Let me explain real quick. The density, or you could say linear density, lambda, Greek letter L, is, remember I said it was kilograms per meter. And so if you times it by meters, it makes sense that you would get kilograms. Also, uh, Oh, and by the way, the density is not the 71, it's not the 90, it's not the 32, it's the average density. So don't stress about it. The other reason this statement makes sense to us here, the other reason this statement makes sense to us is because we know that density is defined as mass over length. So however you want to say it, either the units make sense to you or the definition of density requires it. Either way, I think it's safe to say that density times length is a good measure of mass. Now, this is true on a holistic sense, but it's not practical because there's different densities everywhere. So what we usually do in physics is we say, look, this statement, this idea is good, but it's not practical for us. Let's talk about a micromass, dm, and then we'll say, okay, that's density times dx. So the length, we're not going to use the whole length of the rod. We're not going to use the whole length of the rod. We're just going to use a tiny length of the rod, dx. So we're not going to use the whole length of the rod. We're going to use a tiny length of the rod, dx. We're not going to use the total mass of the rod. No, we're going to use a tiny mass on the rod. So instead of density times length equals full mass, it's density times micro length equals tiny mass. This is a very, very important statement here. Very, very important. And if you take my E&M class next year, boy, oh boy, we use this a lot. Okay, so that goes here, you see. And that's just not obvious. You just kind of need somebody to tell you that. So this part will be a rho dx. Okay, now, what is R? What is R? So if you remember from our previous examples, there were many R's, right? There were many R's. And those R's depend on where the person is standing. Now, this problem is actually a lot easier in one way. There is no actual two-dimensional grid. When the person stands in order to spin this thing, they always stand somewhere on this line. So let's have them stand over here, let's say, at x equals -6. And their job is to attach a rod, we've done this before, right? Attach a red plastic rod and spin this thing around and around. Around what? Around himself. He is the axis. And we're going to spin this big rod around and around. So you can see this is kind of complicated, right? And he doesn't have to stand at -6. I just chose that for fun. You really could have him stand anywhere you like. He could stand somewhere over on the right if you want. Over here, maybe at x equals 12, maybe. But again, spinning the whole thing around his body. Or if you want to, you could have him stand somewhere on the rod. Well, he can't stand on the rod, but he can pretend he's there and spin this rod around itself, you see. And he could stand anywhere, really. So given the location of where the person would stand, that tells you then what is R. So I'm going to go ahead and have my person stand here, x equals -6. As I said earlier, that'll be my axis of rotation. Everything spins around that. Okay, so what is R then? R is not -6. R is not 0. R is not 5. R is, watch close, when you pick your little microscopic piece of mass here, the R is the distance from the person to that mass. So it's basically 6 plus x. See, it's 6 plus x. So right now we're at x equals x. We're not x equals 0. We're not x equals 5. We're not x equals 1. We're at some random x. So it's 6 spaces to get to the rod, and then another x spaces to get to that little dm slice. Okay, so what is r? It is 6 plus x. That's tricky. If he's standing on the other side, if he's standing over here at x equals 12, then your r would be 7 to get to the rod, plus whatever distance this is. So this would be 7, this part. And this, I wouldn't really call it x. I would call it 5 minus x because x equals 0 is actually over here. on the left, right? And then x equals x is right here, and x equals 5 is right here. So it'd be 5 minus x would be that little distance. Okay, let's say that Mr. Shore is just feeling mean, and I want to put my guy over there at 12. It's kind of mean of me, to be honest. And if I do that to you, if I'm being a jerk like that, then what I'd like you to do is pretend that x equals 0 is the other side of the rod. So just make the less dense and the x equals 0. I think that would help. Okay, so for us, it's 6 plus x, and that's what goes here. Let's put it all together. And so this is spinning around x equals negative 6. Make sure you always label which I we're talking about, because remember, you change that person, it changes everything. So there's a 6 plus x, and that's squared. Remember the density function was negative 39 fifths x plus 71. Remember that? That finally gets plugged in there. And now we got this. Don't forget, we will be integrating all of the rod. So the x's range from 0 to 5. And normally with integrals like this, I encourage students to go ahead and distribute first. So there's a 36, there's a 12x, there's an x squared, there's a minus 39 fifths x and a 71. And then we have one more distribute to do. Actually, you know what? Why don't we just type it? You know, just type it, because by the time you get it all done and showing off and doing it all by hand, you're still going to need the calculator to plug in the 5 anyway, because you're going to plug in the 5 and the 0 and subtract, remember. Okay, so I'm just going to do this on my calculator. I have this button ready to go. Let's see here. We got 36 plus 12x plus x squared. That then is multiplied by negative 39 fifths x plus 71. That is an integral from 0 to 5. Okay, I hope I typed that right. The answer is, oh my goodness, it's a big answer. That's a lot of kg m squared. It is a 17759.6 kg m squared. So there's basically a really, really large resistance to rotation here. This is an extremely large rod with an extremely large mass per unit length. This is very heavy stuff, very hard to turn, especially from this far away. Let's talk about it qualitatively for just a moment. If you decide to stand further from the rod, then guess what? This purple number will get bigger. If this purple number gets bigger, then I is going to get bigger. Another way to say that is the further we stand from this rod, the harder it is to spin it around, getting it to speed up or slow down, or if it's at rest, to get it started. So that's how you do a continuous situation. I did a one-dimensional one, and we will learn two-dimensional type of things later in the E&M class, which I really hope you all take. We've got lots of cool gear, lots of fun things to learn. And although the whiteboard often looks really disastrous, we basically are focusing on principles, ideas, and some of those simpler equations when we quiz and test. Except some quizzes, I try to squeeze in some free response, which can get about this hard. So I really am excited for you guys to take that class. We need more people taking challenging courses I almost said UCI. I meant at Villa Park. Okay, so that is your I from an integrals standpoint. And now I think after today's video here, we have a stronger understanding of what I is, how to find it. Last comment. I said that when you have an object, there's anywhere you can stand. You can stand anywhere you like. So it's the last comment here. Give me 30 seconds. If you stand over here, you get a certain I. If you stand over here, you get a certain I. If you stand here, you get a certain I. Of course, there's an optimal place to stand, and that's at the center of mass. And remember, the center of mass is not always at the center of the object. So if you find the center of mass and you stand there, there's still going to be an I, and we call it ICOM. Now, I haven't found ICOM for any of these problems. I never have found an icon. You might think, well, yeah, you did, Mr. Shore. Way back here, you found ICOM when you had this dude standing at the origin. No, that wasn't ICOM. That was I00. There's a difference. Just because I put this guy at the origin does not mean I was finding ICOM. I was finding I00. So that first drawing I made, yes, he's standing here, but 00 is not the center of mass. 00 is an arbitrary place I chose. So yeah, I00, ICM, not the same thing. But there is an ICOM. So on this problem, you'd have to find the COM first and then have the person stand there. Okay, so I want to say this about ICOM. ICOM is really special because let's say you put this on a slippery piece of ice and you kicked it. You kicked it right here with your foot. It's going to spin around and around. It's going to have some center of rotation. Well, that center of rotation will be the center of mass. So in that case, the appropriate I is ICOM. So the center of mass is the place where it will rotate around, and that's just, it's kind of hard to explain, but that's what would happen. And because of that, there's a certain I, and because of that, being at the center of mass, we call it ICOM. So that ICOM is related to I others, other places. So this is really profound. This is in the textbook. Let's say that you wanted to twist this rod around ICOM, right? Let's say that the ICOM is 1472 kg m squared. Remember, it's just a number. It's like a mass, basically. There it is. That's sort of indication that it's pretty hard to rotate or to speed up rotationally. So what you're going to do is you're going to add, so I wrote this wrong. I meant to write I other places. Watch this. I other places equals ICOM plus m h squared. So what am I talking about? So the h is kind of lame. I wish they hadn't picked h as a silly letter. Here's what's happening. We know ICOM is 1472, but suppose we want to shift our green dot over to, so this is ICOM. Let's say we want to shift the green dot over to here, where the rod is much less dense, and we want to spin it around over here. This is called I other place. This distance that we shifted is h. Let's say that this h was, I don't know, 3 meters. And let's say that the mass of this rod, density, weirdness, and all, let's say the mass of this rod is 112 kg, let's say. What we can do is we can say, look, I want to find the I at this other place. And instead of starting all over again with a new integral, I can just take the old ICOM and add on the full mass times the 3 squared. So that's a little bit shocking, like a little bit hard to swallow. And this gives us 2480. So this is called the parallel axis theorem. Parallel axis theorem. And there is, of course, a rule. You can't always use this trick. The only time you can use this trick, of course, is when your axes are parallel. So if you want to walk 3 meters to a new location, this other place, just make sure you still rotate around a vertical line. Don't try to like switch the direction of your green line. Make sure it still points up. And remember, we're trying to spin it around these green lines. So that's a really cool rule. A recap, you can find the I at other places. By the way, even places that are off of the rod, they don't have to be places on the rod or even near the rod. They just have to be a line pointing straight up and down. So you could travel 300 meters if you like, go way past the rod if you like, and you could use this as your other place. And that rule, basically this new rule, allows you to take the old ICOM and just add on total mass times shift squared. And that's just pretty cool. Okay, don't use it often. And remember, com doesn't mean 0, 0. Com means center of mass. All right. If you need the center of mass and they don't give it to you, you have to do another integral for that. So I wouldn't really use this blue rule very often. And it works in 2 dimensions just as well, by the way. So let's say you have a plate right here, and it's really got weird thicknesses, and maybe these are gold atoms and silver atoms and copper and whatever. And it turns out the center of mass is actually here, and then this is your rotation line. And let's say ICOM is 143. And you decide, you know what? I'm going to move this way and this way. I'm going to pick a new spot. This is other. I'm going to draw that line of rotation parallel to the first line. This is going to be my I other. Well, it's going to be 143 plus total mass times something squared. Let's say this total mass is 100 kilograms. So there's going to be a 100 here. Which pink distance do you use? Well, neither. Let's say that this is a shift of 7 and this is a shift of 8. Don't use those. Don't use those. You want to use this. H is here. So do the Pythagorean theorem, you see. 49 plus 80, 49 plus 64 square root 12. What is it? I don't know. Square root of 113. Square root of 113. And that goes here. So it turns out that moving to this new location from the center mass, make sure you start at the center mass for that, not 0, 0. It's basically 100 times 113, which is 11300. And boy, that answer seems kind of big. Do I trust that? That's like way bigger than last time. All right, so assuming I didn't make any errors, I guess going to this other yellow dot is really kind of a dumb idea because you're to rotate this block now around and around, speeding it up in a circle, it's just way harder to do at that other spot. It's so much easier at the COM. And that does make sense. So I just was surprised it was that different. So anyway, doesn't matter if it's 1 dimension or 2. The parallel axis theorem works beautifully. Just make sure you use the red distance, not the 2 pinks. Okay, now the video is done.